Hello, all right, we're going to now look at vector fields. So a vector field like as I said before, we've already looked at functions that take real numbers and bring it to a point in R2 or in R3. And we looked at functions that take a point in R2 and R3, map it to a real number. So now we're going to look at functions that take points in 2D space and map them to new points in 2D space. Or, in other words, for every point in 2D space, it associates it with a vector, a two-dimensional vector. So really, a vector field on R2 is just that. A function, we'll use capital F, and it'll be bold. So if I'm writing it, I'll put a little arrow on top. It assigns to every point in xy in the domain D a two-dimensional vector. So f of xy is going to be a vector with an x component and a y component, right? And a vector field in R3 is going to be the same thing, but just 3 dimensions. So let's take a look let's think about what this would look like. I'm going to put okay, so with a background of a grid, let's try to think about what would this vector field f of xy equals negative yi plus xj look like. So I'm going to plot a few points. Let's start with the point 1, 1 or 1, 0. And the vector here is going to be the vector 0, 1. Okay, so I'm going to indicate that using a vector of that length coming out of that point. Okay, so the point. Let's take the point 0, 1, and the vector that's going to come out of that is going to be the vector negative 1, 0, right? And so that's going to be this vector here. The vector at this point here, let's take a few more points. Let's take this point here. The vector 0, 2, well, the vector is going to be negative 2, 0. And so that vector, I'm going to draw the length here. Take this vector here. Let's take the vector that's at the point negative 2, 1. The vector coming out of that is going to be negative 1, negative 2. And so that's going to be 1 across and then 2 down. It would go down to this point here. And so what you're going to see at these points, at the point negative 1, the vector is going to be 1, negative 1. So it's going to be this vector here. So what you kind of see for this vector field, let's take that point here. This is going to be symmetric, so this vector is going to go. This is going to be the vector 2, 0. So you can see that you have a bunch of points, and you sort of see that you're starting to get this kind of a spirally shape. And what you can do is visualize this with software. You can get a whole bunch of arrows all over the place indicating the vectors, and the lengths will show you the kind of the magnitude of these vectors in space. So here I'm going to actually do exactly that. I'm going to use software. So this is a picture of what this vector field would look like, the vector field negative y, x. You can see you definitely do have this spiral where you have the magnitudes of these vectors increases as you get further and further away from the origin. Here's another vector field. So where the x-coordinate is y. So you can think of it like the arrows when at positive y values, the arrows are going to be pointing to the right, and they'll be pointing to the right proportionally to the y value, and below the x-axis they'll be pointing to the left, and they'll be pointing to the left further and further depending on how far down we go. But the y direction is going to be based on the sine of x, And so you can see that things are happening periodically. We have at pi, at 2 pi, and then over here is 3 pi. I'll show you in the other direction as well, roughly that. So you can see that you do have these kind of these sort of these kind of vortices happening every pi, because the y value is going to depend on x, and so you can see that as you go horizontally across, that the direction is going to go up, down, depending on the So here we have another vector field. This is a little more complicated, where the x coordinate is the natural log of 1 plus y squared, and the y coordinate, or the y component I should say, is the natural log of 1 plus x squared. So you can see these vector fields can have perhaps surprising patterns in them. And software can greatly help you, because you don't want to spend your time graphing out all of these. So let's think about a three-dimensional vector field where f of xy is zk, which is to say, so if we were to look at the for any point, say, let's take the zero vector at the origin. It'll be the zero vector, because f of 0, 0, 0 is just going to be the zero vector, right? F of, let's say, 1, 0, 0 is also going to be the zero vector, because the k component is 0. So f of it really doesn't matter what x and y are. It's just going to be the zero vector for anything on the xy plane. It really just depends on the z value. So if f of x, y, 1 is just going to be the vector 0, 0, 1. Okay, so you'd have, let's put it in red, you kind of have these vectors kind of going up. I'm trying to indicate these, like, sort of, if you can kind of picture them in three-dimensional space, starting around here. Then at these points higher, because the z value is 2, that's the k component. Well, it's going to be going up even more at that point. So what you would have is these vectors that are they're all going to be going up, and then the magnitude of them is going to be proportional to the z value. Of course, down below the axis, if you go down here, they'd be going all down, right? So you'd have this series of these vectors all pointing away from the xy plane. Okay, so let's look at this 3D vector field defined by the vector function y, z, x. So these become very hard to see. I think I'll give it a little bit of a rotation, and you'll start to see the shape of this thing. If I was to kind of view it from up above, you start to see that there's, let's see if there might be I don't think there's a place I can, oh, you can see there are some spirals happening in this. But it's really a lot of a lot of these little vectors really spiraling and looping around. All right, you can see what you get from this thing, and from different directions you can see the spread going in different ways. So here you can see what we're going to get. The horizontally, it doesn't matter where we are. We're always going to have an x component of -2. If I look at this here, or sorry, the y component is always -2. So if I look over this in perpendicular to the y-axis, you can see that always these arrows are pointing to the negative y direction with a magnitude of -2. But I can get to see from up above. There's perspective on this, so but you can see that you've got this spiral along the sorry, if you are ignoring the, let's see, if I wanted to look, let's look perpendicular to the, yeah, you can also see that because the z component doesn't matter, if I look down, directly down on the z-axis, all these vectors are going to be the same regardless of the z value. So you get this kind of these vectors irrespective of the y value, and then the direction. Oh well, let's see. Again, these are a lot of these are going to be hard to see in 3D space. Something like this is useful just to kind of give it a little bit of a rotation. You can start to see. Of course, once it freezes, it's hard. So here's one where this vector field, the x and the y components are divided by a z. So actually, the vector field is not defined when z equals 0 on the xy plane. You can see there's no vectors on the xy plane, so vertically the vectors are going to just kind of be going vertically up and down proportional to it's the z value, z over 4. So you can see above the above the xy plane, they point up a little bit. Below, they point down a little bit. But if you look from above, you have this same kind of spiral that we've seen before. Of course, the spiral changes direction based on the z value. You can see that we're going. I guess you would look at that and you'd see this is clockwise above the xy plane and counterclockwise below the xy plane. So it turns out, so if you have a scalar function like we looked at in previous chapters, f of xy, and you take its gradient, you can see the gradient of f of xy. It's the components of the vector are the partial derivatives f sub x and f sub y. So the gradient of f is a vector field. And we're going to call it a gradient field, in fact. And similarly, if f is a function of 3 variables, a scalar function of 3 variables, then the gradient is a vector field in R3. So let's take this example. F of xy is x squared y minus y to the third. The gradient of f is the partial derivative with respect to x is 2xy, comma, x squared minus 3y squared. So this is the gradient of f, which you can see written like this. It is a vector field. So I'm going to look at the contour map and vector field for this. So here's a sketch of the contour map of this vector field, of the original function, f of xy. And so here is what the vector field would look like. And you can see, if I was to actually overlay the vector field on top, or if I can overlay this, I think it's going to be opaque. You would see. Let's overlay it on the next screen. Okay, so here you can see them overlaid, and what we're seeing here is you can see the gradient vectors are all going perpendicular to these level curves, right? This is something that we've seen before. So the vector field is like this field of vectors going in the uphill slope direction, right? Okay, so now a new definition, a conservative vector field. We call a vector field conservative if it is the gradient of some other scalar function. So if there exists some function f, little f, where this capital F vector field is the gradient of that, then we call it a conservative vector field. And this vector f that is the kind of source of it is called the potential function of f. As an example, the gravitational force on an object is a vector xyz. If the object is at the coordinate xyz relative to the kind of the other object's force of gravity, or that is exerting a large gravitational force with mass m. If the little object has mass little m and the large object at the origin has mass big M, then the gravitational force acting on it is going to be little m big M, then g, this gravitational constant, times the vector x over the magnitude of x cubed. So it's proportional to the it's inversely proportional to the mass. It's inversely proportional to the distance cubed, in fact. So there's a potential function that can generate this gravitational force field, and it's given here, little f of x, y, z, little m big mg over the distance from the origin. That's the potential function. So the gravitational force is a conservative vector field because a potential function exists that generates it. Okay, well, this is it for just an introduction to vector fields. We'll do some more kind of examples of these in class and get some more kind of feeling for what these things look like. All right, bye.